Next, let's do problem 3 on page 140. But before that, I want to explain why I wasn't able to finish the last video. Is because the night before, it was like 11 o'clock or so, and I was ready to go to bed. But I thought maybe I should do one more math problem, you know, and it wouldn't take long. But I was stuck. I don't remember which one I was doing, but I was stuck with it. It had a small problem, and I couldn't figure out. And that I should know how to figure out. And so I was beating around the bush, and the next thing you know, it was 1 o'clock, and I finally got it to come out. But by then it was I was missing my sleep, so the next day I was super tired and couldn't finish the video. And yeah, so that is the reason I tell you that boring story is so that you don't make the same mistake. Okay, and when it's time to go to sleep, please just go to sleep. Let's not do another math problem. Anyway, so that's that, and let's look at problem 3. Problem 3 says something about we have a tetrahedron, okay? And we have to show that the minimum of the sum of the square of the distances of a point. What point is that? This is talking about the point of a tetrahedron. That is, the point is inside the tetrahedron, like this, okay? The P right there. And anyway, so this is the graph I have for it. Anyway, so the tetrahedron is equal to is, you know, whatever it is. We're supposed to calculate the minimum of the distance. In other words, we're supposed to calculate the minimum of the distances of this point to each of the 4 surfaces. A distance squared, of course. Yeah, is something. And we'll figure out what that something is later. But the point is we need to calculate the minimum. Yeah, okay. So to do that, and we have, so what we're going to do is imagine that the tetrahedron is being cut and split into 4 chunks along the red line. That is, the red lines are the point P connected to the vertices. Okay, so there's 4 of them. And so once you cut it along those lines and surfaces, then you get 4 smaller tetrahedrons, you know, that all fit together to become the big one. So that is what we're going with. Okay, so that is what I have. We have, so let A, B, C, D be the 4 surfaces, okay, and the surface areas, all right, and then each one has its distance as X, Y, Z, and U from P. And I used to have small a, b, c, d, but I changed my mind, decided to write it as x, y, z, u instead. All right, so then the volume of this tetrahedron, of course, is the 4 small ones added together, which is 1/3 base area times height, okay? Because each one of these very small letter variables are the heights of the corresponding surfaces, and these are the areas of the surfaces. So V is 1/3 of those 4 things together. So what are we just trying to do here? What we need is find the minimum of the square of the distances. That's these 4 things all squared add up, min f, okay? And under the condition that where G is equal to, what is G? G is equal to ax plus by, well, give me a second here, let me think. Right, G is equal to this equation where V is a given, is a, I don't know what V is, okay? The point is, G is this equation written slightly differently, okay? That is the condition, that is AX, whatever, this will be equal to the volume. Well, we write this thing, then it G equals to AX, etc., minus 3V equal to 0. Now, so we need to solve this thing, and if you look at this carefully, this is exactly the same problem as problem 3 on page 135 that we did a little bit earlier. So, I mean, see? Here's problem 3, right? The only difference is problem 3, f, is subtracted by a bunch of constants, whereas in our case, the a, b, c, d, you can pretend them to be 0. All right, so then G looks almost identical, except E will be the negative 3V that we have, okay? Otherwise, it's the exact same problem, so we can copy down the solution right here, okay? What's the the solution is right here, and we'll just copy this thing down but with A, B, C, and D, the small ones, all 0. Okay, because we're not subtracting anything here. We're just doing x squared, y squared, etc. So plugging this thing in with the top being 0, so that the numerator only has E in it. All right, so let's plug that in into our current situation, which gives us gives this, okay? And what do we have? Then we have this thing equal to, that's the original min f, all right, which is let's see, right. So this is the solution from problem 3, page 135, okay? Now we're going to plug it in with A, B, C, D, the small ones being 0. So we only have the E term left, and the E is negative 3V, right? So it becomes 9V squared because the top is squared, but the bottom is this thing. And this is exact, and so with the end, so we have proven the minimum of F is equal to 9V squared divided by A, etc. squared put together. Now that is exactly what the book says. Now the second half of the problem says is 9 times the square of the volume of the tetrahedron divided by the sum of the squares of the areas of its surfaces. And that is exactly this, right? 9 times the volume of the square of the volume of the tetrahedron divided to the sum of the squares of its 4 surfaces. Anyway, so yeah. So this problem is very short because it's the same one as problem 3 that we already did, and that one was that one was quite hard if you don't do it the right way. So in other words, the grunt work is already done, so we're done with problem 3. The main trick is that you have to cut this thing into 4 pieces, okay, and then put it, imagine, and that's how the volume is represented itself. Other than that, once you notice that, it's really not that big a deal, especially if you already know how to do problem 3 of what are we talking about? Yeah, exercise 3 of the previous section. Okay, so next let's do problem 5, which I forgot to write down. Problem 5 says we need to find the direction of the axis of the ellipse. Some ellipse, the axis of some ellipse by maximizing or minimizing something. All right, so let's do that. The ellipse is okay. So here's the ellipse. Okay, we are going to do it well, like the book, like the way we're supposed to do. We're finding something has something to do with. Does it say anything about the center? Find the direction by minute. Yeah, the distance to the center. Right. So to do that, first we need to figure out what center is. Now to calculate the center of some random ellipse, what you do, there's a standard trick to it. You just take the partial derivative with respect to x and y, and then find out what will solve that solution. Okay. And in this case, it happens to be 1, 1, which is very nice. And then we're going to calculate the max or min of this thing in order to figure out to figure out what the axes are, right? So we'll figure out the max and min of some point, and then calculate the equation of the point from the point to the center, and that should give us the max and the min. Oh, all right. So to do that, we have this. This is the relationship, and then G, the restraint, of course, is the ellipse itself. Okay, and then we'll do the Lagrange multipliers, which is V equals F plus lambda G. We'll go through the grunt work, and we come up with something like lambda equals to that and that, right? Because lambda is right here, and then so well. There might be easier ways to do this, I don't know, but what I did is just, I just said that these two equations are the same, which gives us this big, long, complicated thing that I don't really see how we can make it that much easier, so I wrote it down here, and then I plugged these two things as simultaneous equations into the calculator, and which spit out 4 answers for me, okay? X and Y either equal to that, which turns out to be the maximum if you plug things in here, okay? It's also fairly obvious, I think, that if you plug this in here, those are the max values, are they? I hope so. Yeah, because we're subtracting by 1, see, that's why. And then, or if the signs are flipped, if it's a minus plus and plus minus situation, that will give you the min values. So as a result, so after some cranking, then I calculated that the angles at 45 degrees for the x-axis, for the major axis, and the minor axis is the negative one. Okay, and that should be it. Oh, and I should also show you the graph, how I plug this thing into the calculator, because that was not that easy. And so I would like to show it to you. And it's still just a matter of plugging it into the calculator. See, this is the Wolfram calculus systems equations calculator, which I plugged it in there. As you can see, it solved these two equations. And then the answer popped out. Okay, it's a very good system equation. But I found out that it's not able to do radicals. At least when I tried, it couldn't do it. But well, so this doesn't have any radicals, so we're good. Yeah, so that was. I don't know how tough it would be to solve these two simultaneous equations, but I wasn't interested in trying. Too much work. So plugging it in the calculator and spit it out nicely, and it is right. So that is always awesome. Next, let's look at problem 7, where we're supposed to figure out what is the largest and smallest distance. What? Yeah, I guess. Is that what we're doing? I suppose so. Okay, so here's the ellipsoid, and we need to figure out the largest and smallest distance from 0, 0, 0 to the, which is the center of the thing, I think. And yeah, and no, well, yeah, it is. Well, whatever. The point is, from some point, from the origin to the ellipsoid, which is the largest and which is the smallest distance. All right, so we will, which is a standard problem. Okay, so let's do that. We have the ellipsoid. We need to maximize the distance squared, which is f. Okay, here's the ellipsoid, which is g, equal to this thing minus 1 equal to 0. And then we'll apply the Lagrange multiplier, which gives us identical objects, right? And then which gives us the value, we end up with something like that. Okay, what do you do with that? Well, if x is not 0, all right, so then lambda has to be equal to, from this part, we get lambda equals to minus a squared. Now, if that's the case, then if lambda is that, this equation gives lambda equals to minus b squared, which is not possible, okay, assuming a, b, and c are not the same. Well, or assuming they are the same. Either way, the point is, if it's not the same, lambda can be these things too, which means that y and z has to be 0, if then, right, because this is, because lambda equal to that, it cannot be equal to the others. Now, well, if a, b, and c are not the same. Anyway, yeah. So as a result, that means y and z are both 0, okay? And which means that x, we can calculate then that gives us x equal to plus or minus a, which end up being the minimum or something. Yeah, see, when it's a, then the distance formula, then when you plug things in, then the distance is equal to a at minimum and c at maximum, because we're given that a is less than b less than c. Is that given? Yeah, it says it's given, so they're not the same. So a, b, c are not the same. As a result, that is how we got the answer. Yeah, so that's a fairly straightforward one, except that you do have to notice if lambda is negative a squared, then it cannot be the others, okay? Which forces the others to be 0. I even come up with a second method for this problem, but I'm not going to talk about it because it's no better than doing just this. And so that's, but yeah, you can look at it if you want, okay? And that's, okay, that's enough looking at it. And let's move on to problem number 8. Problem number 8 says that express the number 12 as the sum of 3 parts. 12 equals to x, y, z, and then x, y squared, z squared should be a maximum. All right, so to do this problem, being the y squared and z squared are symmetrical in this problem, the first trick, one I tried, is I simply did it without lambda, okay? I just let y equal to z, set y equal to z, and then we have just 2 equations, right? And plugged it in and took the derivatives and figured out what x is and what that's what x is. Okay, where's y? Well, y is that thing. Well, whatever. The point is, I can't. Okay, y is this. Okay, and x is that. Okay, then I calculate that. And then the second method, then I follow the lambda solution, which actually seems faster than this, doesn't it? Anyway, so I use the standard lambda trick, and have, as you can see, we have a bunch of stuff, and then I got this equation, which means y equals to 2x, and z is the 2x, and x is 12 over 5, and y is 24 over 5, just like the other one. So this Lagrange method does seem better, okay, than the way that I thought I was having a shortcut, but it doesn't look very short, does it? So yeah, so that's either way, but method 2 is probably, the Lagrange method is probably better. I just now noticed that I believe I skipped over problem 2. Okay, so I am going to talk about it right now. At least I don't remember talking about it, but if I did, please skip over this part of the video. But anyway, so problem 2 says that we have, there's a point on the parabola, okay, on the ground, z equal to 0, which is nearest to some plane, and we need to figure out where the point is and what is the minimum distance. So a parabola from the plane, figure out the minimum, where is this closest, okay? Let's see. So here's what I did. Now, the point on the parabola, I did it with 2 ways, okay? First, I'll talk about method 1. That's the non-Lagrange method. That is the way how we would have done before we learned the Lagrange multipliers. So anyway, I did the point of parabola, I did a parametric representation of it, and similarly with point on plane with different parameters, so that the distance, of course, equal to that thing. And then let's move down here a little bit. And then, well, because at that point I thought, oh, maybe I should do the Lagrange method. So I did. So I wrote Lagrange method here. And then I quit that and went back to the original method. So let's look at that for a second. So we have, so f is this. Then the old way, before we learned Lagrange, is when we have a function of 3 variables, and we need to know when is it the minimum or something, right? We just take the partial derivatives like we always do. So we got these things, and then that gives us three equations, which looked very, very hard. Okay, I tried to solve it a little bit and got nowhere. So I pulled out the calculator, which gave me these answers. The systems equations calculator, which gave me t, s, and u equal to the values on the other side over there. And I plugged it into the parabola. So the point on the parabola is 2 minus 2, 0. Point on plane is 1 minus 4, 1. And the distance, when you do this, calculate the 2 points, is square root of 6, which is what the book says it is. Okay, so I got the right answer. And then, before I move forward, I want to show you the systems of equations that I did with the Wolfram calculator systems equations calculator, which I have showed you before. And so here is what happened. See, I typed in the 3 equations in there. Notice the equations are separated by the semicolon, okay? And then things that have spaces in between, like u times t, there's a space between u and t, remember that. And so once I typed that in, and blah, 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 it solved it and gave me a very quick, simple, good, nice looking answer right here, which is how I got it, because I wasn't going to solve that thing by hand. It has t squared in it. Who wants to do t squared? But anyway, so next I decided I will do the Lagrange method as well to see how that works. So I continued the Lagrange method. This is, where's method 2? Method 2 starts about here. I wrote that here, but okay, method 2 starts about here, where point on the parabola is xy with y squared minus 2x equal to 0. Okay, point on plane similarly with different variables. And then the distance squared would be equal to those 2 things subtracting by each other, right? And then the equation v of the Lagrange method would require what does it require? Equals to the function f, okay, plus lambda of the first equation, and then mu of the second equation, which is what I have right here. See, This is the first equation, y squared minus x equals 0. And then, so we have a whole ton of variables here, as you can see. Right. So anyway, moving down here, then now that we have the Lagrange equation, we need to calculate the partial derivatives of everything and partial mu and yeah. What? Let me see here. So I ended up with 5 equations, okay, because I got so many variables, and then things are maybe I didn't need that many equations. Well, whatever. Let's see. Yeah. Well, in any case, the point is I ended up with plus the original 2 things, right? And well, in any case, what I end up having is, and let's look at the next page. I end up with the equations that's identical to what I had before. Okay, these are basically the same as the previous equations from the partial. These things I end up with having to solve these the exact same things like these, which means that to me, at least in my attempt, the Lagrange multiplier doesn't happen to be any better, or maybe even more tedious in this case. So the Lagrange multiplier doesn't always make things easier, but it does a lot of the times. In this case, it really doesn't. Mostly because the function is we don't have to take one variable in terms of the other with a lot of fractions and whatnot, and so it's pretty clean. So we don't need the Lagrange method to make it better, probably. Anyway, so that's all I have to say about problem 2. So next, let's look at problem 12. We have where's my book? We have function z is defined implicitly by 2 functions. The 2 functions, in other words, when you solve them together, their intersection is the function z. All right. We need a necessary condition that z should have a max or min. All right. So that is to find the necessary conditions. We haven't really done that in this section so much, so that's referring to theorems from previous sections. All right, so that is what I have. So first, let's assume partial f partial x is not 0. Then from 1, we are able to pull x out of there as an independent variable, okay, in terms of y and z. This is by theorem 14, page 56. That was the implicit value, implicit function theorem, or implicit something, to show you how you can pull one out. And then, so when you plug x in there, okay, that will become, let's call this new into g. We call this function k of z. And then, so k of z, k of y and z, all right? So then, so we pull the same trick. If the partial with respect to z is not 0, we can pull z out of there, equal to a function y, let's say, like this, all right? So, and then if you take the partial derivative of this thing with respect to, I think, z, okay, then you get this thing, which is the same as partial k partial z, which is not 0. So then, okay, and then next we'll look at theorem B in this chapter, where it says for c equal to a function of y, if partial c partial y is not 0, right, and then partial square, the second derivative, partial c partial y is 0, but the second derivative is not 0, then the max or min for the function z exists. Okay, so that is the necessary condition. So these things, okay, partial f partial x is not 0, and then that partial k partial z is not 0, or something, and then and this is 0, then and the second derivative not 0. Well, anyway, so after all these conditions, well, anyway, I have then the max or min does exist. Well, similarly, we can do the same with if partial f partial x is 0, then perhaps we can assume that partial f partial y is not 0, and get some kind of a y equals x to the see and repeat this process and get these conditions, which we don't normally care about. Okay, we don't care until we fall on our face, then it kind of start to matter. But most of the time, the things it does exist or whatever, and so we'll just take it as it does exist. So next, let's look at problem 13. Problem 13 is says that we have, what is that? Oh, we have two spheres. Okay, you can tell that these things are spheres. I think so. Yeah, they're spheres. There are two spheres in space, and then we have their intersection, right? And we need to, the intersection then is clearly a circle. Well, the question is, where is the circle at the maximum and where is it at the minimum? So to do that problem, what I'm going to do is I will simply define the function f as z, okay? And we're going to maximize z. Z is under the condition of g and h, see? So under these two conditions, when is z maximum, when is z minimum? And that would be the highest and lowest point of the circle, right? So we will plug that in, okay? F is a very simple function, and then we'll use the Lagrange method, which we have lambda and mu, because we have two conditions here, one for each one, and we take the partial derivatives and come down to that. I guess we end up being x equal to y, all right? If x equal to y, then z equal to this thing after, you plug into something. I don't know where. Well, find somewhere to plug it in and figure out z is something like that. And does that matter? I'm not sure. Let's look at the next page. And anyway, so eventually I got z equals to this thing, that's z squared, and then so I end up with these two equations, okay, and then solving these two equations, I got x equal to 0 equal to y, and z equal to 4, or x equal to 2 2/3, then z equal to negative 4/3. So that's the max and that's the min. All right, so that is when you solve those two equations together, I guess. Or just plug one into the other. No, that gives, well, that shouldn't be too bad, but let's not, I wasn't going to bother with it. Either way, you solve that is what happened. Now let me show you the graph. All right, I guess I'll show you this. I did put it in took a screenshot to show you. So here's the system's equation for those two equations that don't look too bad, but you can probably do it by hand, but I wasn't going to bother. Okay, I typed it in and the calculator gave me a very nice answer. Look how beautiful it is. Okay, so that's that. And then the graph of this problem is right here. We have, okay, there is the equation of the graph. We have, first there are two spheres, right? We have, two spheres. And see, there are the two spheres. There's the smaller one, I don't know which one it was, doesn't matter, and the big one. And when they intersect, the intersection is a circle, as you can see. And the next part, I want to show you let's see, make it. All right, that should be good enough. Now, this is all the formulas I used. Okay, that's the small. First, I showed you the big, and the orange circle is this one, and the gray circle is the other one. So anyway, that's the picture on the orange circle. Okay, and then this is the intersection circle when you take away both spheres, as you can, and then the way I plotted this is too hard to. Well, I couldn't figure out directly the easy way to plot out the parametric representation of the circle. So I just used the trick. Okay, I just did this to draw the circle. This thing right here, I used the trick inside Desmos, where I restrained one of the circles. Okay, I restrained the gray circle so that it becomes bigger or smaller. These are the restraints. If you type it in and you see why this isn't actually the representation of the circle. It's just the approximation of it. Let's say. So that is So as you can see, that's the intersection of the two circles. I'll show it to you again. There's the big sphere and small sphere intersection, right? And then when you remove the spheres, then you can see the circle in space. So that is that. And then, oh yeah, and I should also mention the two dots, okay? And I plotted the answer in here, and as you can see, it looks about right. One's on the top of the circle, and one is at the bottom of the circle. Next, let's look at problem 14. We have, let me find my book. What are we doing here? 14 says find the minimum distance from the origin to some surface. Okay, so the distance from the origin is just x squared plus y squared plus z squared. And here's that surface. Okay, we apply the Lagrange multiplier for 3 variables. And then I calculated that lambda equals to 1. And I think everything, if lambda equal to 1, and z is not 0, okay, which gave me some answer. And then if z is 0, however, it gave me a somewhat different answer that was better. So that is the minimum distance, okay? So pick that one. So that one, even though we came up with an answer, that one isn't good enough, because that one's even shorter distance, and we're trying to minimize the distance. And that should be it, okay? And that's problem 14. Next, let's look at problem 15, where we're talking about that same tent that we saw earlier. That was, from what I remember, quite hard to do. But we're going to do it again, and we're going to do it in a different trick, okay? But not with Lagrange multipliers, though. The book specifically says that we are supposed to eliminate y in this in the pack of equations. Here are the two equations. Okay, one is the I don't know, one's the surface area and the other one is volume or something like that. Okay, and but instead of using Lagrange multiplier like we are taught to do in this section, the book says to eliminate y. So what I did is first I tried to use the Lagrange multiplier anyway, and as you can see, that got me nowhere. Okay, I got into a giant mess, and then I stopped. And so the next step, I decided to do what the book says and eliminate y like it wants me to. Now when I did that, then I suddenly found myself with a very interesting situation where I calculated that v equals to z times 1 minus xz, okay, and taking the partial derivative of that thing, that does not get me very far, okay, because that is an odd-looking function that doesn't even go to 0 or something. Anyway, it was unless z is 0, okay. So anyway, I got stuck in a mess, in a weird situation. So the next thing the book says is this equation. It says that something is less than equal to this equation, okay, which is this. If you plug it in, it's going to be less than or equal to x squared. Now, how do we know that? Well, if you multiply this and this out, like here, okay, and you notice that it does check out. This is true. That is, from this equation, which is always true because it's squared, you can work your way back where x squared indeed is bigger than this thing all the time for all x's. So this is true. Now, given that this is true, then let's say x squared is always bigger than or equal to, and being that we're maximizing v, let's say it does equal, okay, because this thing is less than or equal to x squared. Let's say it is equal, because if it's equal, then it will be the maximum for v. So what I did is then I solved for z out of this equation. I got this thing equal to z, and then I plugged it into the v, okay, and then I took the derivative of that, and after some manipulation, I figured out x equal to the square root of 2 over 3, which from this equation then gets me z equals to this thing. Okay, and then I plugged both things into the v and gave me the equation for v equal to that interesting thing. I suppose I could have done that by hand. You know, this equation right here. This is it got smaller there. Here's the equation of let's see. Yeah, here's the equation. This is z. Okay, z times 1 minus x square root of 2 over 3 is x times c. That's the whole v value. So if I could do this by hand, I guess. I don't know. I've never done it before. Probably never will. But anyway, the calculator was able to do this thing rather nicely. This is the Symbol Lab Rationalize calculator. Yeah, you can find it yourself too. Okay, I think I might have, yeah, I have typed it here also under the video. So then the answer V is square root 6/9, which is what we got, which is a very unusual trick of doing stuff. Okay, but well, the book wants us to do that, which is quite nice. And once in a while, you do something that's completely odd. Okay, that is, you know that V has to be less than that. So let's say it reaches it. If it does reach it, then this will be the maximum, and we can't make it reach that value, right? So then, as a result, the maximum of volume is calculated with, and this is much shorter than what we did in the previous section when we did this exact same problem. I don't remember what we did. I just remember that it was very tough. Okay, and we did, I don't know, I had to use the partial derivatives calculator or something, and finally cranked out a amount of formulas and stuff, and this is much neater. Yeah, it's of course the question is, where does anybody think of such a thing? I don't know, somebody do it, and being that somebody has done it, all we have to do is just follow his example. Yeah, so that's problem 15. So next, let's look at problem 16, which says that problem 16, we're doing the same thing as problem 15, okay? We are going to call the surface area F, big F of x, y, z, and then we need to show the F2 equal to 0 at the x, y, and z that we just found. Okay, that sounds straightforward enough. So I have, okay, so here's f of x, y, z, right? We need to figure out what f2 is. I calculated f2, and then we know x and z, we just need to, and v, we just need to figure out what y is from this equation here with x and z in there. So after plugging stuff in, then eventually I figured out that 1 minus x z squared is equal to 1/9 with the calculator. I'll show you that in a second. And we basically just have to show the x squared minus 2y squared equal to 0, right? Because it says we need to prove f2 equal to 0. So y has this relationship here. So we just plug it in, I guess. And once we plug things in, then we realize that the equation for y squared equal to that, it becomes this equation, which is a simple quadratic form equation with identical roots, where y squared equal to 1/3. And therefore, when you plug it in, then f of 2, it does indeed equal to 0, as it says. And that should mark the end of this section.